Okay, so welcome to another video on calculus in a nutshell, and in this video I'm going to be introducing the concept of a triple integral. So far we have seen that double integrals can be used to find the volume between two surfaces. So we know that a surface is essentially represented by a function of x and y. So if we want to find the volume between any two surfaces, all we need to do is we take a double integral of whatever function we're given, or simply we subtract the two surface functions, and that's going to give us the volume contained within it. So to basically formulate the problem of a triple integral, what we will do is we will take a region in space. This is going to be a volume, and we'll call it E. And basically this is going to be analogous to what we did with subtracting the volume underneath one function minus the volume underneath the function under that one, and that gave us the volume enclosed in that region. But what we're going to do is we're going to develop a more general view of this, and we're going to extend this to a higher dimension now. So what we're going to do is we're going to grab a little slice or a little piece of that particular region, and we're going to zoom into it. So what we're going to end up with is a cubic sort of shape. So it's just going to be a little cube, and it's going to have sides of length as follows. So basically this is going to be a little change in the y direction, this is going to be a small change in the x direction, and then this is going to be a small change in the z direction. I'm using infinitesimals just to show you that basically this is just going to be very small portion of that. So what we're going to do now is we're going to call this little cube, we're just going to call it the volume element. And this volume element is just going to be dx times dy times dz, because it is just a cube. But the definition we want to use is not to order the differentials in this form. We actually want them in this form. And this will become apparent in a second when I introduce the triple integral. So what is a triple integral? Well, imagine that we had a function of three variables, x, y, and z. Let's say we have a function of three variables. We already talked about how this is a function that defines a hypersurface in R4. So this is something very abstract. We can't really visualize it because we know that a function of two variables is a surface in three-dimensional space, or simply R3. So that means that if we extend this by one variable, what we're going to do is for any point within this space of three coordinate systems, what we're going to have is we're going to have a point that exists within this R4 space. But obviously we can't really visualize that here. We can't really visualize a fourth dimension. So this is just more of a mathematical abstraction. But let's say that we wanted to evaluate something such as the hypervolume, or beneath that hypersurface in R4. What we would do is we would set up a triple integral like this over the region E. So the region E is the volumetric region within which we're performing that integration. So we're going to have f of x, y, and z times the infinitesimal volume element. And now what's going to happen is we're going to have to define this basically from left to right. We're going to start with x. So basically what we're going to do is we're going to define a region on the xy plane first. And that's going to be basically the shadow that is going to constrain that volume. So that's going to give us the actual walls of that volume. And then we're going to constrain it in three-dimensional space by two surfaces. So the way this is going to work is we usually select two constant limits for the x integral. And then for the second integral, we're going to have limits in y, but we can usually just make them limits as functions of x. So basically what we're going to have is we're going to have, let's call this one y2 of x, and then y1 of x, because we already saw how when we define a region on the xy plane, we can usually do it in this way, and this is the most general way that we can define it. And then for the third integral, or the inner integral, we're going to have two surfaces that are going to constrain that volume in space. And basically what we're going to have two surface functions essentially. and each of these is going to be a function of two variables. So we're going to have z1 xy here, and then we're going to have our function x, y, z. So this is the reason why I originally wanted to set it up in this way, because this, by performing the integration in this order, we can actually start by defining the volume and then integrating that, so that in the end we're just going to have a constant value or a scalar value out of this integral, which is what we want, because we already said that with multiple integrals what we expect to get is a constant value in the end. So we're going to set up the integral like this. So this is what a triple integral usually looks like in Cartesian coordinates. So you can imagine that by analogy to the double integral, this is just going to be a triple sum. So it's going to be equal to the limit of a triple Riemann sum over all those variables. So I'm just going to use shorthand notation here. You can imagine that we just have three infinite sums, and then we're just going to have of the function x, y, z evaluated at each point within that region, and then we're going to have delta z, delta y, and delta x being our finite widths for that little cube that we're using to approximate it. So this is the definition of the triple integral as a Riemann sum. Okay, so now that we have defined this, I think the best way to actually understand how this works is to work out a simple example. So let's say we're given the following function. Let's say we're given the function f of x, y, and z equals to x squared plus y plus z. So this represents a hypersurface in R4. So what we're going to do is we're going to try and find the hypervolume that is enclosed or the hypervolume enclosed within some volume E that we're going to define as follows. So we're going to start with the xy plane. So this is what you should always do. Just start with the xy plane to basically just draw a region D of integration. That region D on the xy plane is going to be the shadow of that volume E in three-dimensional space. So for this example, let's do a simple shape. So this is just going to be a square area, so it's going to go from 0 to 1 on the x-axis and then 0 to 2 on the y-axis. So let's call this D. Now what we can do is we can set up limits for both x and y. So we start with x. X is simply going from 0 to 1. And now y also has constant limits because it's basically this constant function minus this constant function. So it's going to have the following limits, 0 and 2. So that's pretty good. We already defined a region in two-dimensional space. So now let's extend this to three-dimensional space. And what we're going to do now is we're going to draw the exact same region on the xy plane. So we have 1 here, and we have the 2 here, and we have the little region D. And now what we're going to do is we're going to define a region on this three-dimensional space. So to make things simple, let's choose a plane defined by z equals to 3. So that's basically the equation of a plane that is constant along the z-axis. And basically our volume is going to be enclosed by these two. So let's say that z is going to go from z equals to 0 to z equals to 3. So this is going to be the volume that we will call E. And now we can set up limits for z. So this is just going to go from 0 to 3. So now that we have a region of integration, which is a volume, we can actually plug this into the formula and then find the integral of that. So let's do just that. Let me just get rid of this here, just so we can walk through it. So we're going to set up the integral as follows. We have triple integral of our function dv on the region E. So we start with the limits on x, so that's 0 to 1, then the limits on y, that's 0 to 2, and the limits on z, 0 to 3. Our function is x squared plus y plus z, and now we're going to integrate from dz dy dx. Now notice something important. An important remark to make here is that since all of our limits of integration are constant, we could essentially change the order of integration in any way we want, and that would give us the same answer. But that only works when you have constant limits of integration throughout, and that's rarely the case, because essentially when we integrate these things, our region of integration is rarely just a cube or kind of like a rectangular volume. So because this is not something that we actually deal with a lot, we prefer to just perform the integration in this same order. So let's do just that. Let's start by integrating the whole function with respect to z. So we're going to have the following: 0, 2, and then basically treat everything else as a constant, and then integrate with z. So this is going to give us x squared times z plus y times z plus z squared over 2. And now that goes from 0 to 3. And now this is going to become 0, 1, 0, 2. So the 0 is just going to make everything 0. So the 3 is going to go in here. So that's 3x squared plus 3y plus 9 over 2. Now dy dx. And now we're going to integrate this with respect to y. So that's going to give us 3x squared times y plus 3y squared over 2 plus 9y over 2 from 0 to 2, and then dx. So now we're just going to plug those values in, and then we're going to get the following. We're going to have 6x squared plus, so this is going to be 2 squared, that's 4 times 3, 12 over 2, that's 6. And then 2 here cancels out, so that's 9. So this becomes 15. And then in the end, we're going to integrate with respect to x. So this is going to become 2x to the power of 3 plus 15x from 0 to 1. And finally, that's going to give us 2 plus 15, which is equal to 17. So this is equal to 17, basically. And now, this is a really, really important concept, because triple integrals are used quite a lot in physics and engineering. And the reason for that is that they're usually used to represent something like the mass or the density of a particular volumetric region. Now, that's sort of a more physical type of interpretation of this. In mathematics, what a triple integral designates, or what it represents, is just the hypervolume underneath a hypersurface in R4. And because that's such an abstract concept, we don't tend to use triple integrals a lot in that definition. We tend to use them more for applications like calculating mass, volume, or density. And that's something that we might do in later examples. Another remark that I want to make about triple integrals is that if you make f a constant, so let's just get rid of this here. If you make f a constant, what you're going to find from that triple integral is the volume of that region E. So let's say we have an integral of this form. The function is just 1. So what's going to happen is you're going to be calculating directly the volume of that region E. So why is that? Well, let's try and figure this out. Let's do the definition again. AB, then y1x, y2x, and then z2 xy, z1 xy, and then our element of volume is going to be dz dy dx. So because there is just a 1 here, we know that we can easily integrate this with respect to z, so that's going to give us the following: AB y1x y2x. So this is going to be z evaluated on these two limits, so z2 z1 dy dx. And something very peculiar happens here, because as you might imagine, what we're going to end up getting is the difference between those two surface functions So we have two surfaces. We're going to be subtracting them from each other, like this. And then we're going to perform a double integral on that. And if that reminds you of anything from double integrals, you would know that this is actually the volume. This will give you the volume between two surfaces. So this is why this particular definition is basically represents the volume of that region. So that's a really, really interesting. It's pretty much the same, but this is kind of where this comes from. So there's a nice connection between those two definitions there. So this is quite useful for calculating the volume of some abstract region that is defined by whatever parameters we choose. And just to show you that that's the case, let's try and find the volume of that region we just calculated. So a region was basically just a sort of like a cube. So we have the x-axis 0 to 1, y 0 to 2, and then on the z-axis we had 3. So this is our region E. Now if we find the volume of this region simply by using multiplying all the lengths together, that's going to be 1 times 2 times 3, that's 6 units cubed. So would we get the same answer using the triple integral? Well, we should expect so. So let's just try and do just that. So let's have V equals to 0 to 1, 0 to 0, 3 of dz dy dx. So that's going to give us is the following. So we're going to have 0, 1, 0, 2. This is going to be set, and we're going to evaluate it from 0 to 3. So that's just going to be 3 dy dx. And now when we integrate this is going to give us 3 times y, and then we're going to evaluate it from 0 to 2. So that's going to give us 6. And then in the end, we're going to get the following. This is going to be 6x, and that's just going to be 6 units cubed. So yes, we obtained the exact same value from that. So that's just a really nice application of integrals. And obviously this gets a lot more complicated for when we have regions that are not necessarily of this shape. We can have virtually any shape we can think of. We can have something like a pyramid or a tetrahedron of some sort. And obviously that complicates matters quite a lot, because that means that we no longer have constant limits of integration. So obviously our function is going to get increasingly more complicated. But that's something that we will deal with in the next video. We're going just to look at different examples with different regions of integration, and then we're going to apply some transformations of coordinates just to simplify things for certain cases.